Welcome back, everyone, for another deep dive. Today, we're going to be looking at deep learning,
Okay.
which is something that I think a lot of people have heard about, but maybe don't fully understand how it all works.
Yeah, it's definitely a hot topic in the AI world these days.
Yeah, so we're going to try and break it down today. We're going to look at a research paper that explains all the different ways that these machines can learn.
It's a really comprehensive paper. It covers everything from the basic concepts to some of the latest advancements in the field.
Yeah, and we're going to try and make it fun and understandable for everyone listening along. So get ready to learn about algorithms, neural networks, and how deep learning is being used in all sorts of crazy applications.
Like, how about recognizing your face to predicting the stock market?
Yeah, that's right.
Yeah.
So let's dive in. What exactly is deep learning?
Well, it's a type of machine learning that's inspired by the human brain.
Okay.
It uses artificial neural networks to analyze data and learn from it.
So these neural networks are like little mini brains inside the computer.
Kind of, yeah. They're made up of layers of interconnected nodes that process information, kind of like neurons firing in the brain.
And the deep in deep learning refers to the number of layers in these networks.
Exactly. The more layers a network has, the more complex patterns it can learn.
So it's like the deeper you go, the more intelligent the machine becomes.
You could say that, yeah. And that's one of the things that makes deep learning so powerful. It can handle really complex data sets that traditional machine learning methods would struggle with.
Okay, so that brings up a question I've always had.
Yeah.
I keep hearing about how deep learning needs massive amounts of data to work well. Why is that? I thought more data would just make things harder.
Well, with traditional machine learning, we have to manually extract features from the data and then feed them into the algorithm. That can be really time-consuming, and it doesn't always capture all the nuances of the data.
Right.
But with deep learning, the neural network can learn those features automatically, directly from the raw data.
So it's like the machine is doing the heavy lifting of figuring out what's important in the data.
Exactly. And that's what makes it so effective, especially when you have these huge, messy data sets that are common in the real world.
Okay, that makes sense. So let's talk about some of the specific techniques that are used in deep learning. One that I'm particularly interested in is word embeddings.
Oh, yeah. Word embeddings are really cool.
Can you explain what they are?
Sure. So basically, word embeddings are a way to represent words as numbers.
Numbers.
Yeah. It might sound strange, but it's actually really clever. Each word gets assigned a unique vector of numbers that captures its meaning and its relationship to other words.
So like cat and dog would have similar vectors because they're both animals.
Exactly. And cat and tractor would have very different vectors because they're completely different things.
Okay, I'm starting to see how this could be useful. But how are these word embeddings actually created?
Well, there are different techniques, but one of the most popular is word2vec. It analyzes massive amounts of text to learn how words are used in context.
So like the machine is reading a ton of books and articles and figuring out how words relate to each other.
Exactly. And once it's learned those relationships, it can create these numerical representations that capture the meaning of words in a way that computers can understand.
Wow, that's pretty impressive. Can you give me a real-world example of how word embeddings are being used?
Sure. Imagine you're running a business and you want to analyze customer feedback from online reviews.
Okay.
Word embeddings could be used to automatically identify the sentiment of each review, whether it's positive, negative, or neutral. This could give you valuable insights into customer satisfaction and areas for improvement.
That's a really practical application.
Yeah.
I like it. Okay, so we've talked about word embeddings. What about recurrent neural networks, or RNNs? I've heard those are good at understanding sequences like sentences.
You're right. RNNs are specifically designed to handle sequential data where the order of the elements matters. Think about a sentence, for example. The meaning of this sentence depends on the order of the words.
Right.
RNNs have this special ability to remember previous inputs, which allows them to understand the context of a sequence.
So it's like they're reading the sentence word by word, but they're also keeping track of what they've read before.
Exactly. And that allows them to understand the meaning of the sentence as a whole.
Okay, so that's RNNs. What about LSTMs? I feel like I've heard that term somewhere before.
LSTM stands for long short-term memory, and it's a type of RNN that's particularly good at remembering information over long periods of time.
Okay, so it's like an RNN with an even better memory.
Exactly. And that makes it really useful for tasks like language translation and speech recognition where you need to remember information from earlier in the sequence.
Makes sense. You know what's funny, though? The name LSTM sounds really familiar. Like I've encountered it in my everyday life.
Well, you probably have. Think about your phone's autocorrect feature.
Oh, yeah.
It seems to get better at predicting your next word over time, right?
It does, yeah. It's almost creepy sometimes.
That's because it's probably using a deep learning model with LSTM to learn your writing style and preferences.
Whoa. So every time I'm texting, I'm basically training a deep learning model.
Pretty much, yeah. It's learning from your input and using that information to make better predictions in the future.
That's pretty amazing. Okay, so we've covered word embeddings, RNNs, and LSTMs. And we're just getting started with deep learning. Where do we go from here?
Well, there's a whole world of deep learning techniques out there, but maybe we can move on to recursive neural networks. They're a bit different from RNNs, but equally fascinating.
Okay, I'm intrigued. Lead the way. So recursive neural networks, they sound a little intimidating.
Maybe a little, but they're actually pretty cool once you get to know them.
Okay, I'm ready to get to know them. What are they all about?
Well, they're really good at handling hierarchical data, which is basically data that's organized in a tree-like structure.
Like a family tree.
Exactly, or the branching structure of a sentence.
Okay, I can see how that could be relevant to language.
Yeah.
But how do these recursive neural networks actually work?
So they process data in a recursive way, meaning they break down complex structures into smaller and smaller parts until they reach the individual elements.
So like taking a sentence and breaking it down into phrases, and then breaking those phrases down into individual words.
That's a good way to think about it.
Yeah.
Yeah, and as they're breaking down the structure, they're also learning the relationships between those different parts.
Okay, so they're not just understanding the individual words, but also how those words fit together to create meaning.
Exactly. And that makes them really powerful for tasks like natural language processing and sentiment analysis.
Can you give me a real-world example of how they're being used?
Sure. Imagine you're scrolling through social media and you come across a post claiming that a certain celebrity has passed away.
Okay.
How do you know if it's true or just a rumor?
That's a good question. With so much information flying around online, it's hard to know what to believe.
It really is.
Yeah.
And that's where recursive neural networks can come in handy. Researchers are using them to analyze the spread of information on social media, looking at how text and images are shared and how people are reacting. By understanding the hierarchical structure of these online conversations, these networks can help identify patterns that indicate whether a piece of information is likely to be a rumor or a credible news story.
Wow, so they're like digital detectives helping us sift through the noise and find the truth.
You could say that, yeah. They're using their understanding of hierarchical structures to make sense of the complex world of online information.
That's really impressive. Okay, so we've got recursive neural networks for understanding hierarchies. What about neural tensor networks? They sound even more complex.
They are a bit more complex, yeah. But they're also really powerful. Neural tensor networks, or NTNs, are particularly good at capturing the relationships between different entities.
Entities?
Yeah, like people, places, things, concepts, anything that can be represented as a data point.
Okay, so it's like they're building a map of how different things are connected to each other.
That's a good analogy. And they use tensors, which are mathematical objects that can represent multidimensional relationships to capture those connections.
Okay, I'm going to be honest. That sounds a bit over my head. Can you give me a more concrete example of how NTNs are being used?
Sure. Let's say you're building a facial recognition system.
Okay.
Traditionally, these systems focus on analyzing facial features, like the distance between your eyes or the shape of your nose.
Right.
But what if you could also take into account things like your age, your gender, or even your emotional expression?
I guess those things could help distinguish between people who might have similar facial features.
Exactly. And that's where NTNs come in. Researchers are using them to combine facial recognition features with other attributes like age, gender, and emotions. By capturing the relationships between these different types of information, they're able to build more accurate and robust facial recognition systems.
So they're like teaching the computer to see the whole picture, not just the individual parts.
Precisely. They're helping the computer to understand the context and the relationships between different pieces of information, which is something that humans do naturally.
That's fascinating. Okay, so we've covered recursive neural networks and neural tensor networks. What about these hybrid neural networks? Is that what it sounds like, combining different types of networks?
You got it. It's like creating a custom deep learning solution for a specific problem by combining the strength of different models.
That's pretty cool.
Yeah.
So it's like assembling a team of experts, each with their own unique skills, to tackle a complex challenge.
I like that analogy.
Yeah.
And the possibilities are endless. You could combine a convolutional neural network, which is great at image recognition, with a recurrent neural network, which is good at handling sequences.
So, like, you could have a system that can watch a video and then generate a text description of what's happening.
Exactly. Or you could have a system that can analyze medical images and then predict the likelihood of a patient developing a certain disease.
The potential is pretty mind-blowing. Okay, so hybrid neural networks are all about teamwork. What about generative adversarial networks, or GANs?
Yeah.
I feel like those are getting a lot of attention these days.
They are. They're one of the most exciting and talked about areas of deep learning right now.
Why is that? What makes them so special?
Well, GANs are unique because they involve two neural networks that are pitted against each other in a kind of AI battle.
A battle. That sounds intense.
It is. One network called the generator is responsible for creating data like images or text. And the other network called the discriminator is responsible for evaluating that data, trying to determine whether it's real or fake.
So it's like a game of cat and mouse where the generator is trying to fool the discriminator and the discriminator is trying to catch the generator.
Exactly. And as they train against each other, both networks get better and better. The generator learns to create more realistic data, and the discriminator learns to become a more discerning critic.
That's pretty clever. So what are some of the things that GANs can do?
Oh, the possibilities are pretty much endless. They can generate realistic images of people and places that don't even exist. They can create music and art. They can even translate languages.
Wait, they can create things that don't exist. That sounds like something out of science fiction.
It kind of is, but it's also very real. And it's just one example of the incredible power of GANs.
Okay, so we've got GANs creating realistic images and all sorts of other cool stuff. What about capsule neural networks? I've heard those are trying to improve upon traditional convolutional neural networks, or CNNs.
You're right, CNNs are great at image recognition, but they have some limitations. They don't always do a good job of understanding the spatial relationships between objects in an image.
So like they might recognize a nose, eyes, and a mouth, but not understand that they're arranged in a way that makes a face.
Exactly. And that's where capsule neural networks come in. They're designed to encode information about the pose and orientation of features, which allows them to understand those spatial relationships.
So they're like CNNs with a better sense of spatial awareness.
You could say that, yeah. And that makes them really good for tasks like object detection and image segmentation.
Okay, so CapsNets are all about understanding the bigger picture, not just the individual parts. What about the attention mechanism? That's another term I've heard thrown around a lot lately.
The attention mechanism is a game changer in deep learning. It allows neural networks to focus on the most important parts of the input data, just like we humans do when we're reading or listening to something.
So instead of trying to process everything equally, the network is learning to prioritize the information that matters most.
Exactly. It's like when you're reading a news article. You don't read every word with the same level of attention. You skim through and focus on the key sentences and paragraphs that contain the most important information.
Right.
The attention mechanism allows neural networks to do the same thing. It helps them to filter out the noise and focus on the signal.
That's really cool. So how is this attention mechanism being used in real-world applications?
It's being used in a wide range of tasks, including machine translation, text summarization, and even image captioning. For example, imagine you're using a language translation app. The attention mechanism could help the app to focus on the most relevant words and phrases in the source language when generating the translation.
So it's like having a translator who knows exactly which parts of the text to pay attention to.
Exactly, and this can lead to more accurate and natural-sounding translations.
That's amazing. Okay, so we've covered a lot of ground in this deep dive, from word embeddings to GANs to the attention mechanism. It's incredible how many different techniques are being used in deep learning.
It is, and we're only scratching the surface. The field is constantly evolving and new techniques are being developed all the time.
It's really exciting to see how far deep learning has come in such a short amount of time. But now I'm curious to know, what are some of the limitations of deep learning? Are there any challenges that researchers are still trying to overcome?
That's a great question, and it leads us into some of the really important considerations for this field.
Okay, let's dive into that. It's really exciting to see how far deep learning has come in such a short amount of time. But now I'm curious to know, what are some of the limitations of deep learning? Are there any challenges that researchers are still trying to overcome?
That's a great question, and it leads us into some of the really important considerations for this field. One of the biggest challenges is the sheer computational power that's needed to train these models.
Yeah, I can imagine, especially with those massive data sets we talked about earlier.
Exactly. Training a deep learning model can take days or even weeks, even with powerful hardware. And the energy consumption can be significant too, so there's definitely a push to find more efficient training methods.
That makes sense. So computational power is one challenge. What else is on the list?
Another big one is interpretability, often referred to as the black box problem. Deep learning models can be incredibly accurate, but it's not always clear how they arrive at their decisions.
So we know they work, but we don't always know why they work. That seems a little unnerving.
Yeah, it can be. And it's a big concern, especially in fields like healthcare, where we need to be able to trust the model's judgment.
Yeah.
If a model is diagnosing a patient, we need to understand the reasoning behind that diagnosis.
Absolutely. So researchers are working on ways to make these models more transparent.
They are. There's a lot of research going on in the area of explainable AI, which aims to make these models more understandable to humans.
That sounds like a crucial step. Okay, so we've got computational power and interpretability. Any other challenges we should be aware of?
Another one is robustness. Deep learning models can be very sensitive to changes in the input data. Even a small change can sometimes throw them off completely.
So they're not very adaptable.
Not always. And that's a problem because the real world is full of unexpected variations and noise. Researchers are working on ways to make these models more robust so they can handle those real-world conditions.
That makes sense. We want them to be reliable even when things get messy.
Exactly. And then there's the issue of bias. Deep learning models are trained on data, and if that data is biased, the model will be biased too.
So like if a facial recognition model is trained on a dataset that's mostly white faces, it might not be as accurate at recognizing faces of other races.
Exactly. And that can have serious consequences in real-world applications. So there's a big push to make sure that the data used to train these models is diverse and representative of the population as a whole.
That's really important. We don't want these powerful tools to perpetuate existing inequalities.
Absolutely. So those are just a few of the challenges that researchers are grappling with. But despite these challenges, there's a lot of optimism about the future of deep learning.
Yeah, I can see why. We've seen how it's already transforming so many different fields.
Exactly. And as research continues, we can expect to see even more amazing applications of deep learning in the years to come.
Well, this deep dive has been truly fascinating. We've explored the inner workings of deep learning models, from those that understand language to those that generate art. And we've even glimpsed the challenges that researchers are working to overcome.
It's been a pleasure diving deep with you.
And to you, our listener, thanks for joining us on this journey. We hope you've gained a new appreciation for the power and the complexity of deep learning.
Remember that world of possibilities we talked about? Analyzing customer sentiment, detecting rumors, creating stunning images, and even building self-driving cars. Those are just a few examples of how deep learning is shaping our present and our future.
It's a field that's full of surprises, and we can't wait to see what breakthroughs emerge in the years to come.
Keep exploring, keep learning, and keep asking questions. The world of deep learning is vast and ever-changing.
And who knows, maybe you'll be the one to make the next big discovery. Until next time, keep diving deep.